Yeah, we're very happy to introduce our final speaker for the conference, Stefan Willigenburg, who will be telling us about Schur functions and non-commuting variables. So take it away, Steph.
Wonderful. Well, thank you very much to the organizers for organizing this fantastic conference, and thank you all for coming. So, as I was explaining to the organizers, my plan is going to be similar to that of Ina and Natasha's in that I'll be giving the talk, and then my postdoc and co-author, the wonderful Fareed Al-Naifad, is going to be answering your questions in the chat. So what I'm going to be doing is I'm going to be telling you today about Schur functions in non-commuting variables. And if you don't know what any of those words mean, don't worry, we're going to explain all of them as we go along. So let's get started. So we say an integer partition, lambda1 greater than or equal to lambda2, and so on, then is going to be a list of positive integers whose sum is n. So for example, 3, 2, 2, 1 is a perfectly nice integer partition of 8, since 3 plus 2 plus 2 plus 1 is 8. And then if lambda is equal to lambda1, lambda2, and so on, then we say lambda factorial is going to be lambda1 factorial, lambda2 factorial, and so on. So if we go to our running example right here of 3, 2, 2, 1, then lambda factorial is going to be 3 factorial times 2 factorial times 2 factorial times 1 factorial, which is going to be 24. And if instead we write our partitions as 1 to the number of 1s, 2 to the number of 2s, and so on, then lambda to the factorial is going to be your number of 1s factorial, your number of 2s factorial, and so on. So again, going back to our running example, we know that 3, 2, 2, 1 can be written as 1 to the 1, 2 to the 2, 3 to the 1, and therefore lambda to the factorial is going to be 1 factorial, 2 factorial, 1 factorial, which is 2. And then with this in mind, well, we're now going to look at set partitions. We've seen them earlier in the conference. Let's just recall what they are. So a set partition of the numbers 1 up to n is a partitioning of the numbers 1 up to n into disjoint sets that are going to be called blocks, such that no block is empty, and the union of all the blocks is going to be the numbers 1 up to n. So, for example, 1, 3, 4, 2, 5, 6, 7, 8 is a set partition of 1 up to 8, since, well, none of these sets are empty, and the union of all of them is 1 up to 8. And what we're going to do is we're just going to simplify our notation. So we're just going to drop these braces, we're going to just drop those commas, and just write our sets 1, 3, 4, 2, 5, 6, 7, 8. Then with this in mind, given your favorite set partition pi, then we say that lambda of pi is just going to be all of the various block sizes written in weakly decreasing order. And so, for example, if pi is 1, 3, 4, 2, 5, 6, 7, 8 that we saw on the previous slide, then, well, lambda of this is just going to be block sizes in weakly decreasing order. So 3, 2, 2, 1. And then given a permutation, we say that delta of pi is just going to be, well, you're going to let delta act on the first block, then delta act on the second block, and so on. So if delta is 1, 4, 3, 2, 5, 8, 7, 6, then delta of pi is going to be the following. Well, 1 goes to 1, 3 goes to 3, and 4 goes to 2, giving us 1, 3, 2. Then 2 goes to 4, and 5 goes to 5, giving us 4, 5. 6 goes to 8, giving us 8. And then 7 goes to 7, and 8 goes to 6, giving us 7, 6. And then if we just tidy up our set partition so that each of the blocks increase left to right, and then we'll order them by least element in each block, we're going to get 1, 2, 3, 4, 5, 6, 7, 8. And so now what we're going to do is we're going to take the slash product of two set partitions. So if you have two set partitions, pi and sigma, then the slash product pi slash sigma is going to be, well, you're just going to write down pi. And then if pi is a set partition of n, you're going to take the first block of sigma and add n to every element, write it down, second block of sigma, add n to every element, write it down, and so on. So let's do an example. So if pi is 13425 and sigma is 123, then their slash product pi slash sigma is going to be, well, we just write down 13425, and then since that's a set partition of 5, we're then going to write down 1 plus 5, which is 6, 2 plus 5, which is 7, and 3 plus 5, which is 8. And that's going to be the slash product. And so with this in mind, we're now in good shape to define the algebra of symmetric functions in non-commuting variables of Rosas and Sagan. So there's Mercedes Rosas, and there's Bruce Sagan, who I saw in the audience too. And so this is in their beautiful paper that was published in Transactions, and if you haven't read it, I highly recommend it. And in it, they introduce a number of bases for this algebra, and in fact, E pi has actually been defined before. It was defined by Margaret Wolf in her 1936 paper that appeared in Duke, in which she was looking for a non-commutative version of the fundamental theorem of symmetric functions. So let's have a look at the bases of Rosas and Sagan. So the first one is going to be the monomial symmetric function in NC-Sim. And this is going to be a sum of monomials, xi1, xi2, and so on, such that the variable in the jth position is equal to the variable in the kth position if and only if j and k are in the same block of pi. So for example, if we wanted to compute m132, then since 1 and 3 are in the same block, this means that our variables in the first and the third positions have to be equal. And then the second one has got to be different. So we're going to get terms like x1, x2, x1, x2, x1, x2, x1, x3, x1, x2, x3, x2, and so on. Then the second basis we're going to have is going to be that of power sum symmetric functions in NC-Sim. And this is going to be the sum of monomials xi1, xi2, and so on, such that the variable in the jth position is equal to that in the kth position if j and k are in the same block of your set partition pi. So if we wanted to compute P132, then we know that since 1 and 3 are in the same block, then the variables in the first and the third positions have to be the same. So things like x1, x2, x1, x2, x1, x2, and so on. But you could also have that all three variables are the same. So you're going to get terms like x1 cubed, x2 cubed, and so on. Then the elementary symmetric function in NC-Sim is going to be, well, again, we're going to have ourselves a sum of monomials, xi1, xi2, and so on. But now we have that the variable in the jth position is different from the variable in the kth position if j and k are in the same block. So, for example, if we want to compute E132, then this time, because 1 and 3 are in the same block, the variables in the first and the third position have got to be different. So we're going to have terms like x1, x1, x2, x1, x2, 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 x1, x2, x1, x1, but of course you can also have all your variables being different. So you can have terms like x1, x2, x3, and so on. And then our last basis is going to be somewhat more intricate, but it's going to be the one that's going to be the most important. But this is basically the most intuitive definition that we came across. Okay, so this is going to be the complete homogeneous symmetric function in NC-Sim, and this is going to be a sum of those monomial symmetric functions in NC-Sim along with a coefficient. Now, how do you compute this coefficient right here? Well, this thing here is going to be the maximal set partition, and we'll do an example in a second, where every block is a subblock both of sigma and of pi. Once we've done that, we're going to take lambda of it and then take its factorial. So let's have a look at an example. Say we want to compute H132. Well, notice that the set partition 132 is a maximal set partition where every block is contained in 1, 2, 3, and every block is also a subblock of 132. This is also the case of 132 and 132. Then note that 1, 2, 3 is going to be the maximal set partition where every block is a subblock of, well, 1, 2, 3 and 1, 3, 2. This is also the case of 1, 2, 3 and 1, 3, 2, and of 1, 2, 3 and 1, 3, 2. So now we've computed these. Well, we take this one now and we take lambda of it factorial. So we just take 2 factorial since there are 2 things here, and then 1 factorial since there's 1 thing there, multiply them together to give 2. And then that's going to give us the coefficient 2, and thusly 2m, 1, 2, 3, and 2m, 1, 3, 2. Similarly, if we do this with 1, 2, 3, we get 1 factorial times 1 factorial times 1 factorial, giving us a coefficient of 1, m, 1, 2, 3. We also get m, 1, 2, 3, and 1m, 1, 2, 3. Now, with this in mind, we're going to give you a couple of facts. So if we have some permutation and we have that delta of m pi is equal to m delta of pi, then for your bases being the power sums, the elementaries, or the homogeneous, you get that delta of b pi is equal to b delta of pi. And if you have 2 set partitions, then for your bases being the power sums, the elementaries, or the homogeneous, you get that b pi times b sigma is equal to b pi slash sigma. So let's have a look at a couple of examples. So if we take m, 1, 2, 3, and let the permutation 1, 3, 2 in one line notation act, well, that's just going to swap the 2 and the 3. So we're going to go from m, 1, 2, 3, swap the 2 and the 3, and get m, 1, 3, 2. If we now look at this product right here, then p, 1, 3, 2 times p1 is going to be, by this definition right here, p, 1, 3, 2 slash 1, which by our definition of slash product is going to be p, 1, 3, 2, 4. Now, why were these functions so called? Well, if we let the variables commute in our algebra NC sim, then what we get is the algebra of symmetric functions sim. Do you know what that is? That's wonderful. If not, you can take it as a definition. And so with this in mind, if you let the variables commute in our monomial, power sum, elementary, and complete homogeneous symmetric functions in NC sim, then what you get out is the monomial, the power sum, the elementary, and complete homogeneous symmetric functions. And these are the classical ones in sim. And so a natural question to ask is, where are the Schur functions? So for this, what we're going to need is we're going to need some diagrams. So given your integer partition, then the diagram of it is going to be the array of boxes with lambda I boxes in row I from the top. So this is going to be English notation. So if we take our running example 3, 2, 2, 1, we're going to have 3 boxes in the top row, then 2 in the second, 2 in the third, 1 at the bottom, and then we're going to left justify them. And then with this in mind, we're now going to make dotted Young tableau. And so we say a dotted Young tableau of shape lambda is going to be a filling of the boxes with the numbers 1, 2, 3, and so on. So the rows weakly increase as we read them from left to right, and they strictly increase as we read them from top to bottom. And then you've got dots that are appearing 1, 2, 3 up to the number of boxes once and only once. So this is an example of a dotted Young tableau, because notice that our rows weakly increase as we read them left to right, strictly increase as we go top to bottom, and we have 1, 2, 3 dots. And then given a dotted Young tableau, we can associate a monomial to it. So we say the monomial associated to it is just going to be, well, we're going to put xi in position j if and only if I has j dots above it. So going back to our example here, we have 2 has 1 dot above it, so we write down x2 first. Then 4 has 2 dots above it, so we'll write down x4 second. And then 1 has 3 dots above it, so we're going to write down x1 first. Then with this in mind, we can define the Rosa-Sagan-Schur functions as follows. What you're going to do is you're going to take all dotted Young tableau of shape lambda, then you're going to make the monomial corresponding to it, and then you're going to add them all up. So if we wanted to make the Rosa-Sagan-Schur function S21, then what we're going to do is we're going to need to make all the dotted Young tableau of shape 2, 1. Here are all of them down here that have 2 1s and 1 2. And then we're going to make the monomial corresponding to it. So here we're going to get x1, x1, x2. Here we're going to get x1, x1, x2, thusly giving us 2, x1, x1, x2. This is going to give us x1, x2, x1. This will also give us x1, x2, x1, giving us 2, x1, x2, x1. And then finally, these two are going to give us x2, x1, x1, and x2, x1, x1, giving us 2, x2, x1, x1. And then Rosas and Sagan were able to prove the following. They were able to show that the Rosa-Sagan-Schur functions are linearly independent, and when you let the variables commute, then you get the classical Schur functions. However, they're not a basis for NC-Sim because we only have one for each integer partition rather than set partition. So they asked, is there a way to define functions for set partitions that have properties analogous to the ordinary Schur functions? And the good news is yes, there is. So now it's time to go on an expedition and have an adventure. So it's going to be taken by the 3 musketeers, who are Farid Al-Niraifad, Xu Shaoli, who I was totally unable to find a photo for, and myself. And so for this, what we're going to need is we're going to need a non-commutative version of Leibniz's determinantal formula. And here's Leibniz's house right here. It's going to be exactly like the Leibniz determinantal formula you know and love. So you're going to have a sign of a permutation. That's perfectly normal. But now what you need to do is take your product of entries in a certain order. It's got to be taken from the top row to the bottom. And that's really important. And so with that in mind, the source Schur function then is going to be S lambda, which is going to be the non-commutative determinant of, well, our complete homogeneous symmetric function in NC-Sim, indexed by 1 up to lambda I minus I plus j, along with a coefficient 1 over lambda I minus I plus j factorial. So let's have a look at an example. So if, say I want to make the source Schur function S21, then I'm going to have the determinant of this matrix right here, which is going to be 1 over 2 factorial h12 times 1 over 1 factorial h1 minus 1 over 3 factorial h123 times 1 over 0 factorial h empty. And then that's going to give me a half h12/1 minus a 6 h123, which by our product rule is going to be a half h123 minus a half h123. But we've only got an integer partition, so we've got to ramp things up to set partitions. So we're going to do this using Tableau. And what we're going to do is we're going to make Tableau such that every element 1 up to n appears exactly once. The rows as you read them go from increase from left to right. And then if you have 2 rows of the same length, then the first column increases top to bottom. Then the blocks of our set partition are going to be in 1-to-1 correspondence with the rows of our Tableau. So if we look at this set partition right here, we see 1, 3, 4. It's our biggest block. We put it in the top row. Then we see 2, 5, and 7, 8, the same size. 2 has the smallest element, so we put 2, 5 first, then 7, 8, and then we put 6. And now we're going to create a permutation in the following way. We're going to read our elements by row, and that's going to give us our permutation in one-line notation. So we're going to get 1, 3, 4, 2, 5, 7, 8, 6. And if we recall our special way of writing set partitions from the previous slide, which was also 1, 3, 4, 2, 5, 7, 8, 6, then you can actually swiftly go from pi to delta pi just by dropping these set signs. Then with this in mind, the Schur function in NC-Sim is going to be, well, S pi is going to be our source Schur function S lambda of pi, and then we're going to let delta pi that we saw on the previous slide act. So let's do an example. So if pi is 1, 3, 2, then by definition t pi is 1, 3, 2, and thusly delta pi is 1, 3, 2. So then our Schur function in NC-Sim S132 is going to be, well, we take our source Schur function S21, we let 132 act on it. We computed this on an earlier slide. It was a half H123 minus a 6 H123. We're going to let 132 act on that. That's going to allow 2 and 3 to swap. So we just swap 2 and 3, giving us a half H132 minus a 6 H123. And then with this in mind, we actually do get ourselves a basis for NC-Sim. And just as we would want, if you let the variables commute, you recover the classic Schur functions. And if you take your source Schur function and let delta act on it, and that's going to be over all partitions in your symmetric group, and you're going to add them all up, you actually recover the Rosa-Sagan Schur functions. Now, the sad thing is unlike those other bases, delta of S pi is not equal to S delta of pi in general. Now, you might think that that's a bad thing, but it turns out to be an absolutely great thing, because what happens is you actually end up getting for each permutation delta a whole new basis of NC-Sim, such that when you let the variables commute, you get the classical Schur functions, which is pretty sweet. So what we're going to do now is we're going to ramp things up to Rosa-Sagan skew Schur functions. Now, for this, we're going to need skew diagrams. And so a skew diagram is going to be the array of boxes contained in lambda, but not mu, if we're making the skew diagram lambda skew mu. So for example, if we want to make 5, 3, 3, 2 skew 2, 2, 1, then what we're going to do is make the diagram 5, 3, 3, 2. Then we're going to locate 2, 2, 1 in the top corner, and then we're going to just cut it out. Then with this in mind, the Rosa-Sagan skew Schur function is going to be the following. What you're going to do is you are going to take all your dotted Young tableau of shape lambda skew mu. So again, you're going to have your rows being weakly increasing, your columns strictly increasing, and then you're going to throw on 1, 2, 3, etc. dots. Then you're going to make the monomial corresponding to it, and then you're going to add them all up. The only difference is going to be that instead of being of shape lambda, you're now going to do this in something of shape lambda skew mu. So then, with this in mind, well, if you take the Rosa-Sagan skew Schur function and you let the variables commute, then what you end up getting is you end up getting the classical skew Schur functions. And that's not all, because if you then wanted to write your Rosa-Sagan skew Schur functions as a sum of Rosa-Sagan Schur functions, then you get some really beautiful coefficients. And those are positive, they are integers, and they're exactly what you would hope they would be. They are in fact the classical Littlewood-Richardson coefficients, which remember is the way of expressing the classical skew Schur functions as a sum of classical Schur functions. And so the last thing I'm going to talk about in my last couple of minutes is going to be the algebra of non-commutative symmetric functions of Gelfand, Krobbe, Lascaux, Leclerc, and Thibon. And we're also going to be talking about a map that was defined by Nantel-Bergeron, Reutenauer, Rosas, and Zabrocki. So, well, what are these non-commutative symmetric functions? Well, these are just going to be the sum of all monomials in non-commuting variables, xj1, xj2, and so on, where these indices weakly increase. And our map J is going to take these things right here to 1 over n factorial times our complete homogeneous symmetric function in NC sim indexed by the set 1 up to n. And so with this in mind, then the immaculate functions of Berg, Nantel-Bergeron, Saliola, Serrano, and Zabrocki, those get mapped under J to our source Schur functions. And similarly for the non-commutative ribbon Schur functions of Gelfand et al., these then get mapped to the ribbon source Schur functions, which are just natural generalizations of our source Schur functions. And so with that in mind, here ends our algebraic combinatorics virtual expedition. So all that remains for me to say is thank you very much for listening. And since this is the last talk, thank you very much to the organizers for such a wonderful conference. Let's thank the organizers. Thank you very much.
So yeah, let's also thank Steph for a wonderful talk. And before we move on to the poster session and such, are there, of course, any questions for Steph that weren't already taken care of by Fareed in the chat?
So
also thank you to Fareed. We should give him a round of applause because I've just seen the number of questions. I couldn't have finished my talk on time without him. So please, let's also thank Fareed for a question.
So have you considered doing generalization of the other interesting bases, those with parameters like Hall, Littlewood, and etc.?
That is a wonderful question. Yes, we haven't got to that yet. It is on our wish list though. Yeah, fantastic question. Thank you. That would be amazing.
Great. Any other questions?
So you found these Littlewood-Richardson coefficients coming up in the skew non-commutative Schurs expressed in the Schur basis. What about the product of two non-commutative Schurs? Do you still get the same sort of identities?
Oh, that's a great question. I've just saw other questions. Per Alexanderson, is there a dual Jacobi-Trudy? Yes. And also yes to Maria's question. It's not the Littlewood-Richardson rule, but it's the one where if you take the product of two Schur functions, then it ends up being the sum of the two skew Schur functions, the one where you place one on top of the other and the one where you place one next to each other. That one still holds. And that actually is crucial to taking your products from the top row to the bottom row. So that was another thing we found.
Cool.
Thank you.
So there's also some questions that are popping up in the chat. So I think the first one was Per, who asked, is there a dual Jacobi-Trudy?
There is indeed, because Rosas and Sagan defined omega that takes the h's to the e, so you can apply that. And the cool thing is you get a totally different basis again. So awesome question, and yeah, that's what happens.
Great. And then Richard asked, are there some nice non-commutative Schur positivity results?
Again, on the wish list, that is a fantastic question. So yeah, we really are hoping that we'll find something soon, but we don't have too much at the moment. It's at early stages. But we do have a representation theoretic interpretation. That's one thing in the direction of positivity. And again, it's spec modules. So thank you.
And then Per asked again, is there a non-commutative Cauchy identity?
Oh, fantastic question. Okay, I'm going to start writing all of these down. Excuse me. Wonderful. We have not found one yet, but we should definitely look. That's a great question. Yeah. Thank you very much, Per.
And then finally, Ben asked, is there a Schubert calculus interpretation?
Oh, fantastic question again. So yeah, thanks, Ben. So definitely, again, open. We haven't looked at it yet. So, you know, Travis Scrimshaw also asked us again about flagged. Wonderful questions. We haven't looked into that. This is literally hot off the presses. It went on the archive 2 weeks ago, maybe. So fantastic question. Yeah, amazing if there was something like that, but we don't know yet. Thank you.
And then a new one just popped in. So Nate asked, is there any hope of extending imminent conjectures to this setting?
Ooh, fantastic. Yeah, we don't know that. That's something we haven't looked into at all. This is wonderful. Thank you. Got so many new things to look at. We haven't looked at that yet, but that's an amazing question. Thank you.
That's great. Great. So if there aren't any other questions or stuff, let's thank them one more time. So. And yeah, also let's give all of our speakers for the whole conference one final round of applause. So thank you very much,